Hello and welcome to the APL quest. See APL Wiki for details. Today's quest is called Float Your Boat. We are to select the numbers from a vector of numbers that are floating point or non-integers. This is problem 7 from the 2013 APL problem solving competition. It's a bit of an interesting thing that it's not well defined what exactly constitutes a floating point number or a non-integer number. Because in APL, a number is a number. There's not really any good distinction. But we'll do our best, and any of these solutions would be considered correct. Let's start off by creating some data for ourselves. What constitutes a number that isn't an integer? Well, there are various ways to approach this. A very simple one, and probably the best method really, is to compare the number to what would happen to it if we were to round it. So any number that's integer stays the same when rounded, and any number that isn't integer would change. So the floor of this vector gives us these integers, and then we can compare, and these gives us the integers, but we're actually interested in the non-integers, so let's go change that. And then we can use this to filter, and this gives us the non-integers. We can put this into a function. Let's call that f, and use the name of the argument, and there we go. Somebody who participated in the live chat event noticed that this can actually be written as an entirely derived function, not even a train, but a tacit derived function. That is a function that's entirely composed of operators and functions together. And we can see how we can transform f into such a thing. So let's have this tacit form. First, we want to compare the argument with its own floor. So the way we can do it is we want to use the function unequal dyadically using the same argument on both sides. So that means we need a selfie or commute operator here. And let's get rid of some of this noise. And then we want to preprocess the right argument to unequal using the floor, keeping the left argument just the outer argument itself. So this places the same argument on both sides, we floor the right side, and then we feed it into unequal. I like to think of the jot or compose or beside as preprocess the right argument. So this is unequal while preprocessing the right argument with floor using the same argument on both sides, and we can use that to filter. And so this is the same pattern again. We have this filtering function, and we want to use the same argument, but the right side is preprocessed by this function, and the left argument is just the way it is. So we can do the same thing again. So we use the preprocessing the right argument operator with parentheses like that, and then use commute to put the same argument over on both sides. So this is a fully tacit version of f. However, I don't consider this very readable. It's perfectly correct. It's more for exercise sake that we do this conversion. Now, as I mentioned, there are some interesting questions regards to what exactly is considered a non-integer and what exactly do we mean by floating point. Let's create some interesting data. Let's say we take a very small value, 1 times 10 to the power of negative 13, and we add it to the numbers 1 through 15. If we print these numbers, then they look like integers, and that is because by default APL will round to about 10 digits of precision, and then because we've only added 10 to the power of negative 13 to each one of these, we don't notice this. However, if we format using 14 decimals, then we can see that there is actually more to it. We could also, of course, say W minus the floor of W, and then we can see that there's a bit of a difference there. It isn't exactly ones, 1 times 10 to the power of, and that is because there are some floating point inaccuracies at that level. And this is where things get a bit interesting. Should these numbers in W be considered floating point or not? Well, if we try to apply a function f on W, then you can see it says, oh, the numbers 1 through 9 are considered non-integers, but the numbers 10 through 15 are considered integers, which is, of course, interesting and odd. The reason is that APL by default has something called the comparison tolerance, which is a multiplicative fuzz factor, allowing comparison as long as the ratio to each other does not differ by more than 1 to the power of negative 14, or 1 plus 1 to the times 10 to the power of negative 14. This fuzz factor can be set, the comparison tolerance, but this is the default value. And that is why I chose 1 times 10 to the power of negative 13. So as soon as we hit 10 or more, then we now reached the factor of 14 orders of magnitude, and their numbers are considered equal. So when we're comparing the floor with the original number, they are now considered equal, and therefore they are filtered away. Now we can counteract that by making a version of f, let's say the comparison tolerance including version, where we temporarily and locally set the comparison tolerance to 0. And after that, we use the formula as before. Now, when we use FC on W, then all 15 numbers are considered to be floating point, because we are now exact in what we are doing. So this is one definition, that they compare to each other. Another definition is the internal representation. Normally in APL, you don't care much about how things are represented internally, unless possibly you're doing some performance optimizations, but usually not for the values themselves. But we can actually ask APL, what is the data representation of such values? And then if we go back to V, we can see that V, which we have here, is stored as a 645. 645, the 64 means a 64 bit per element, and 5 means it's floating point, a binary floating point. So this is a 64-bit binary float array. However, quaddr also tries to compact every argument you give it before it tells you what the data type is. And if we apply quaddr on each of these, then we can see that trying separately on each element to compact them as much as possible, the first number can fit in a 64-bit float only. The second number, 4, can fit in 8-3. That means 8-bit, and 3 means integer, so that's an 8-bit integer or 1-byte integer. And we can exploit this then. We can create a function g that selects the argument filtered by whether or not 645 is equal to the data representation of each element. And this will work on V. And if we try it on W, then we'll see that it also considers all these numbers to be floating point values, because they're in fact stored as floating point, even when they're compacted the most, because they have this additional 1 times 10 to the power of negative 13 added to them. So here, comparison tolerance doesn't matter at all. And let's make for an interesting one. If we take the values from V and we also add a very large value, and it should be noted that if I ask what is the data representation of 1 times 10 to the power of 400, it answers 1287. This is not a 64-bit float, because 64-bit floats do not reach such large magnitudes. Instead, it is a 128-bit float, and the 7 here indicates that it's not a binary, that would be 5, and 3 is integer, but rather a decimal float. So this is using a 128-bit decimal float representation for the large magnitude. And of course, this gives a problem. So now we have our x, And if we try to run g on x, then things fail spectacularly. And the reason is that APL will internally upgrade all of these numbers to be decimal floats, and then they get stuck there, and we compare them. So if we say the data representation of each one of x, then we can see that the floats all became decimal floats, and the integers are filtered away, of course. And then since we're only looking for binary floats, we're not finding anything. But we can amend this function. So let's say we have a g which is also tolerant for decimal values, and for that we just check for membership in 645 or 1287, and now we can run gd on x, and it matches all of these. So this considers 1 times 10 to the power 400 a floating point, which is correct as to the internal representation. However, the problem specification also said non-integer, and I'm sure you'll agree that 1 times 10 to the power 400 is very much an integer, not a non-integer. But this depends on how exactly you understand the problem. So a very simplistic understanding would be, from a human perspective, well, it's an integer if it's just a bunch of digits together, possibly negative, and it's not an integer if you need a decimal point in order to write out the number. And we can write this in APL as well. So what we'll do is we'll format each number to a character vector, and then we can look whether or not there is a dot in each of these. And if there's a dot in the character representation of the number, then it would be a non-integer number. This is not going to work when you use this scaled format with an e inside, but for normal numbers, it's going to work. We can also combine these two. Instead of running two loops, we can fuse the loops by saying we want membership, but we want the right argument to membership to be pre-processed with format. So this is a dot member of the format for each one of the numbers, and if there's a dot, then we want them, otherwise we discard them. So we simply filter by that, and now we can try this on x, and we can see that the 1 times 10 to the power 400 is going to be filtered away. However, if we run x on our w from before, remember w were these numbers from 1 to 15 with a little bit added, it considers none of them to be non-integers. So it's, in a way, it's more tolerant of being close to integer. And the reason for that is because when we format the numbers in w, they look like this. But we can actually give a left argument to the format function, which is the number of decimals to add. So if we add, say, 14 decimals to it, then we can see that we get this 1 at inside the decimals. So we could amend the function to do this. If we ask for too much, then it's going to add some underscores for digits that it cannot figure out based on the internal representation. Another way is using something called the print precision, which by default is 10, which is why we by default will get 10 significant digits in our printouts. And if we change quad pp to something large, say 17, then doing the same expression will give us more. So there's an implicit argument to the format function. Let's change that back to 10 here, and then we can write our function h as before, but this time we make a local change to pp, and I'll set it to the maximum value that's allowed. Even for decimal floats, it will be 34 digits. So we take omega, filter that with whether or not a dot is a member in the format of each of the argument. And now we can try it on w, and now it considers all these near integers to be non-integers. I should probably have given this a new name. I'll do that in the code that I post. Okay, and so much for regular ways. Let's look at a little bit more exotic ways of solving this problem. Here's one. Let's say we have these numbers v. We can take the division remainder with 1. So this is also known as modulus 1, or what is left over if I was to try to create this number just by adding ones together, and that is a non-integer if the number is non-integer, and 0 if it is an integer, because you can create any integer by multiplying an integer with 1, of course, that same number. And that means that we can compare with 0. So wherever we have 0, we want to get rid of that, and whenever we have a positive value, non-zero, then we want to keep it. So we could you do just a comparison with 0. However, we can also just take the sign or signum of this, because we'll never have a negative result from the division remainder modulus. And so this gives us our mask, and we can select the values based on that. Let's put this into a function I. There we go. And now we can try it on these values. So here we can see we hit this problem again with near integers. And we could solve this by changing the comparison tolerance locally. So let's do IC with comparison tolerance. So we can set that to 0, and then we have the same formula as before. IC on W, and now it works for all these values. And then there's a tricky thing, which is the represent or encode. And encode with a takes a, so encode is the down tag. It takes a possibly mixed radix on the left and represents the number or numbers on the right as in this base. However, here we're not actually interested in a full representation. We're not even interested in any representation. The only thing we want to know is that if the smallest unit in the base is a 1, then would there or would there not be a 1 there, and how many 1s would there be? It's a bit interesting to explain like this, but let's have a look at what it looks like with v. And we can notice that this is exactly the same as the division remainder, which actually makes sense, because when you're trying to convert to a base, then you keep subtracting as large units as possible, and then the remainder is left over here. So what's happening here is that how many ones are there that cannot be represented in a larger unit, and then we end up with a division remainder. Now, what's interesting with encode is that it doesn't care about comparison tolerance. It's always precise. So we could actually abuse this and write it exactly the same way without specifying comparison tolerance, and then it would work even for these near integers. However, I don't think this is very clear. Don't write this in your production code. It's much better to set quadct to 0 to tell the reader what is you're actually trying to do. Another way to work around it is, remember I mentioned that quadct is like a multiplicative fuzzy factor, and it's used to measure relative difference between things. Now, if you multiply by 0, of course you get 0. And the consequence of this is that any comparison with a true 0, the comparison tolerance doesn't matter. So even a value that is very, very small, say 1 times 10 to the power of negative 300, is not going to be considered the same as 0. How can we use this? Well, if we take these values and we subtract their floor, like we spoke about in the beginning, and then we can compare this to 0. And this gives us also a true comparison. So we can write now a subtraction-based version of f that uses this system. And we can try fs on our special w, and oops, sorry, this is wrong. This should be an unequal, of course. We want the ones that are non-floats. There we go. And we can see that all of these near integers are now considered to be non-integers. And that is because the difference between them and their floor is very small, but but is not equal to 0. And finally, just for a bit of a joke solution, if we try to use the argument as left argument to replicate, but we're not actually interested in using any value, so we can just replicate the empty vector, which will always give the empty vector. Then the function is subject to the limitations in domain of the replicate function. Now the replicate function can take any integer, positive or negative, including 0, as argument. This means that it will error if any element is not an integer. And that's exactly what we're looking for. So we can set up a error guard that says that if any error happens, it's really a domain error, but let's just do any error for now. If any error happens, that means that the test that the argument is non-integer and we want it. Otherwise, we replicate the empty vector, which gives us the empty vector. Let's try this first. So if we do this on v, then we can see the gaps here. So we get an empty vector for every for every integer, and we get the integer and we get the number itself for numbers that are not integers. And all we need to do now is enlist, and that collapses all the empty vectors away, and we just get the result we want. This solution also works. It has horrible performance, it's completely abusing the system, and it fails on numbers of very large magnitude. But, well, it works. Subject to comparison tolerance, again, like before, and we now know how we can deal with that if we want to. But that's it. Joking solution, please don't do this.